All right, so linear equations. What are we going to do today? There's really just a couple things. We're not going to do 4 and 5. We're just doing 1 and 2 today. I want to show you two different kinds of equations for a line, and we're just going to practice using those a little bit. Okay, so what is a linear relation? Really straightforward. A linear relation is any kind of a relation that connects inputs and outputs in a way that makes those inputs and outputs, if I plot those points, they line up in a linear fashion. So they all fall on a single line. Big deal, right? Okay, how do we deal with lines? Well, we have to represent lines with equations. There are two ways we can do this that we're going to talk about today. There's one other one that we'll introduce a little bit later. But today the two we're going to talk about are slope-intercept form and standard form. Give me a 1 to 5 on standard form. Okay, you guys think you remember standard form? You may be a little familiar with it. What's standard form? That's the one I'd be surprised if a lot of people remembered it, because you probably haven't used it very much. No, it's a way that we write linear equations. Well, here, I'll tell you what, let's cheat. Let's skip ahead. There's one that I guarantee you do know. Slope-intercept form. Y equals mx plus b, right? We'll get back to that one. That's the most common one. And we'll talk about that one in just a second. That's one way of writing the equation of a line. That's the way we usually want to end up. We want to typically write our answers for most of the rest of the year. When you solve a linear equation, when you want to simplify a linear equation, it's going to say write your answer in slope-intercept form, almost always. Okay, so that's usually where we want to end up. There's another kind of linear equation that we use sometimes too, the standard form, and here's standard form. Standard form is not y equals mx plus b, it's ax plus by equals c. Now where a, b, and c are just going to be some numbers, okay, but there are some rules for standard form. When we write equations in standard form, we want to follow 3 rules, but I'm going to take one of them off the table because it's kind of a dumb rule. So first of all, a, b, and c are integers. Okay, well, even that one eventually is going to go away. They don't have to be integers, but for our purposes this year, they are going to be integers. But in future years, we might even relax that rule and say, no, they don't have to be integers. They could be irrational numbers, or they could be something like that, right? Or they could even be, they could be irrational numbers. It could be like pi, or the square root of 2, or something like that. But for now, we're not going to worry about that. That's a later on thing. For this year, they have to be integers. What's an integer? We talked about that a while ago. Remind me. What's an integer? Give me examples. That might be easier. Give me examples of integers. Somebody name an integer. 1. 1's an integer. What's another one? What is it? No, 4/3 is not an integer. How come? Okay, because it's not a whole number. Integers are a little bit bigger than whole numbers, but you're on the right track. So 1 would be an example of an integer. Give me another one. 2. What's another one? Okay, give me a bigger one. 100, okay. Give me a different kind of integer. -8, okay. You're starting to get the hang of this, right? -20, -8, -3, 1, 8, 200. What do those all have in common? Okay, they're numbers, right? But if we write them as fractions, what's the denominator? 1, okay. So they're fractions. They are the fractions that have a denominator of 1. Does that make sense? And then also the one that sometimes people forget about is the one that's in the exact middle. What's that? 0. 0 is also included. So another way to think about integers, and I almost think like this is maybe the easiest way, if you think back to the number lines that you've drawn for years and years and years, integers are the hash marks on a number line, right? 0's in the middle, and then it goes 1, 2, 3, 4 forever. In the other direction, -1, -2, -3, -4 forever. So there are all those hash marks that we put on the number line, okay? So A, B, and C, we want them to be integers. We don't want them to be fractions. Okay? There's one. The next rule that sometimes people apply, but it's a dumb one, is that A has to be positive. Well, we're going to get rid of that one. It's more convenient to make A positive, but it's not wrong if A is negative. So we're going to go ahead and make it positive, but again, it's not really essential. And then the other rule that is very important is this one. So let's number these. We've got rule 1. They're all integers. And rule 2, the greatest common factor of A, B, and C is 1. Okay, what's that mean? If you're trying to explain that to somebody who's not as far along in math as you are, maybe your younger sibling or something, how would you explain that to them? What's it mean that the greatest common factor of those numbers A, B, and C has to be 1? The what? Okay, that's very good. That's really close. By share, what do you mean? The biggest number that goes into them has to be 1, right? The biggest number that divides evenly into all 3 has to be 1. Does that make sense? Okay, we'll see some examples and it'll clear it up. Okay, so let's do a couple things. Oh, and by the way, why do we do this? Raise your hand if you're a little annoyed with math for always having, but you don't even have to know why, you're just annoyed with math in general. If you're a little annoyed with math for always having these multiple ways of doing the same thing, like here we have 2 ways of writing an equation. Does that seem annoying? Maybe, right? There is a reason for this though. The reason that we want to have multiple ways of writing equations is that it depends on what we want to do with them. If we're trying to just graph an equation, well, it turns out that's a pretty good way to write it in slope-intercept form. That's ideal for graphing an equation. This is different. Standard form is not so much, it's really not very convenient for graphing an equation, but what it's really good for is something we're going to do next unit. What it's good for is if I've got multiple lines and I want to solve a system of linear equations. So I've got more than one lines at the same time, and I want to find the x and y values that make all of those lines true at the same time. That's called a system of linear equations. And the best way to write a system of linear equations, the easiest way to deal with them, is if I write all the linear equations in standard form. So there is a reason for standard form that we're going to need next unit. That's why we're talking about it now, so we get a little practice. Okay, let's look at a couple examples here, and we're going to write these in standard form. So look at number 1, everybody. Okay, do I have to do anything to number 1 to put it in standard form? What do you think? No, I really don't. I really don't. What's the one thing that we could do to make it slightly better, even though that's correct? Remember, the one thing, it's not really a rule, but the one thing that we wouldn't mind doing here is making A positive. Not a rule, but it's a good idea. So how could I, in equation 1, problem number 1, what would I have to do to make A positive to both sides of the equation? Well, okay, so I could move everything to the opposite side of the equation, right? And that would work, but that's a lot of stuff to do. There's one thing I can do in one step that's a little bit easier. Divide everything by -1, or, which is the same as multiplying everything by -1. What's 6 divided by -1? -6. What's 6 times -1? Okay, they both do the same thing, don't they? Which one's a little bit easier? I'd say multiply. Here's why, because it's easier to show the work. Like if I want to, in number 1, if I want to, let me rewrite this. So here's the equation, -5x plus 6y equals -12. Well, look how easy this is. If I just distribute a negative, which is the same as distributing -1 to all the terms in that equation, what's that do if I distribute a -1? What's that do to each term? Okay, but what's it do? I mean, what's it do to make them different? It's going to do something consistent. What's it do to each term if I distribute a -1? What's it change about each term? The sign, right? That's all it does. It just changes the sign of each term. Everybody see that? So that's a really common thing we do in math a lot of times. Distributing that negative then is just going to make that first term change. It's going to switch it from negative to positive. Second term, it's going to switch it from positive to negative. And on the other side, it's just going to switch it from negative to positive, and that's what we end up with. Okay, give me thumbs on that. Does that make sense? Okay, that's one of our tools we use in math a lot, is just distributing a 1 through the entire equation to change all the signs. Okay, what else? What about number 3? Can anybody see something we need to do there? I got to add 24 to both sides. Good. Because I need it to look like standard form. Remember, it looks like a number times x plus a number times y equals a number on the other side. Good. So we add 24. I like it. If we add 24 to both sides, those guys cancel, and I get 9x plus 6y equals 24. Done? Anybody see anything else? Ah, there it is, right? What's the other rule? The other rule is we said, remember, that the greatest common factor of A, B, and C, of all the coefficients, has to be 1. Well, there is a number other than 1 that divides into 9, 6, and 24. And what is it? 3. Yeah. So I have to divide each side through by 3, which means I'm just dividing each term by 3, right? So what's that give me? 9 over 3 is 3. 6 over 3 is 2. So I get 3x plus 2y equals 8. Okay, there we go. Now we got it. Make sense? Okay, how about number 5? What's obviously wrong with number 5? Fractions. Got a bunch of fractions. You're right. So let me rewrite this. This is good practice because we've done a lot of this stuff in the past, but, you know, we need a little review maybe. Okay, so remind me, how do I clear fractions in an equation like that? No, I can't just flip them. What do I have to do? To clear fractions, I have to multiply by what? The least common multiple, but what is it? What am I trying to, so it's going to be, how do I, what is the number? 12. Why is it 12? That's right. Okay, because 12 is the smallest number that all of the denominators divide evenly into, right? Everybody get that? Okay, so that's the GCF, right? So we're going to distribute a 12. Okay, now remind me how we do this, because we were really smart about this. We did this in a way that was, we simplified it. Do I multiply straight across by 12 over 1 and then reduce? Do I multiply first and then divide? No, what do? Divide first and then multiply, right? We're going to reduce first and then multiply. You guys are you remembering this? So 12, that really is technically 12 over 1, but we don't even need that. What is 12 divided by 4? 3. Okay, so that's going to cancel out. I'm going to reduce that fraction. I'm going to cross the denominator out, and it reduces to 3, which I then multiply by the first term, but the denominator's now gone, right? So all that's left is the numerator, so 3 times 3 is 9x. Remembering that? Does that make sense? Okay, what about the next term? What do I do? Okay, so you tell me. Okay, 12 over 3 is 4, so we cross the denominator out. And what am I left with? Okay, minus 4y equals 1? 12, because I have to distribute there also, don't I? 12 times 1 is just 12. Okay? Give me thumbs. Does that bring it? We've done that lots of times, but it's been, been a little bit since we did that, right? How about this one? What's one thing I definitely have to do? Okay, I'm going to have to do that. True. What do I maybe want to do right away to make this look easier? Yeah, clear fractions. So everybody show me on your fingers, what am I going to have to multiply through that entire equation? Yeah, okay, I'm seeing it. What's it going to be? 6. You bet. 6. Okay, so if I multiply everything by 6 and I distribute that, well, what happens if I distribute 6 to the first term? 6 over 6 is 1. Okay, so I'm just multiplying the top by 1. Well, what's 1 times 1? 1. So I get 1x. How would I write that? 1x is just x. Good. 6 times y is going to be 6y, and 6 times negative 2 is negative 12. Good. Almost there. What's the last thing I have to do? Okay, I got to push the y term over to the left side, right? I need the x and the y terms on the left side and the number on the right side. Okay, so we're going to subtract that 6y from both sides, and that just gives you my answer. X minus 6y equals negative 12. Okay, good? Give me thumbs. How we doing? How we doing on that? Or give me 1 to 5. I really want a little feedback here so I know how we're doing on this stuff. I just need to see you as a class, like, okay, okay, all right, okay, well, we'll get some more practice. All right, slope-intercept form. So we already said it's y equals mx plus b. What if I wanted to write that in function notation, like we were doing the other day? What's the only thing I'd have to change? What does function notation do to a regular equation? What do I do? Yeah, right? All I do to make it function notation is I'm just going to say, instead of y, I'm going to swap the y for an f of x, just a fancy name for y, right? That's it. Okay, so we could do it either way. Usually we would just do it the first way. If we're graphing an equation, we usually want to use y, so we just say y equals mx plus b. Okay, so now remind me, why do we call this slope-intercept? What does m stand for? Slope, right? So hence the name. What does b stand for? Okay, what do we call that? Where on the y-axis it crosses. What do we call that? The y-intercept. Okay, so there's the name, slope-intercept, right? That's why we call it slope-intercept, because those are the two ingredients for a line that's written in that form, m and b. So what's that mean? Well, let me ask you this. If I have an xy plane up here, how many lines could I possibly draw in the infinite xy plane? How many lines are contained? An infinite number. Yeah, there's an infinite number of different possible lines that I could graph in the xy plane. I mean, how do I choose one compared to the others? Like if I want to pick a specific line out of all the infinite possibilities, what do? Well, really all I have to do is dial in a specific number for m and a specific number for b. And if I do that, if I dial in specific values for those two, we call those parameters in math, which means they're special numbers that by choosing them we get to change the equation. If I pick specific values for m and b, I'm going to specify one line, one single line out of all the infinite possibilities. Okay, so let's talk about those two numbers then, the slope and the y-intercept. Remind me about slope. How does slope work? It's rise over run, yeah. Okay, so if I've got 2 points then, like if I've got in the xy plane, if I've got 2 points, I've got a blue point right here and I've got a red point over here, and I've got a line that goes through those 2 points. You told me that slope is rise over run. Well, what does that mean? Explain rise. What's rise? Okay, so if I'm going to go from the first point, which is the one that's furthest on the left, to the second point, which is the one that's furthest on the right, the rise is just how far, if an ant has to go from blue to red, the rise is how far the ant's going to move vertically. Agreed? Okay, so the rise then would look like that. He's going to go up by that amount. That's my rise. Okay, what's the run? How much it goes horizontally. Good. So how far is it going to the right? So this is the run. So how are we going to define that? Well, if I had coordinates, it'd be easy to do, right? Like, for example, you got to watch this really closely and you'll make this connection here. Like if I had, for example, the point, let's say this one were over 2 and up 1 from the origin. So the coordinates of the blue point were 2, 1. And let's say the coordinates of the red point were 4, 2. What would the rise be? I disagree. It'd be 1. How come? Okay, because I'm going up 1. How do you know from the coordinates that you go up 1? Okay, because the y coordinates are changing by 1, aren't they? Right? The ant's going from a blue point that has a y coordinate of 1, which means it's up 1 from the x-axis, to a red point that has a y coordinate of 2, right? Well, the y coordinate is telling us the vertical positions of the points. Agreed? So if the y coordinates are increasing by 1, then that means the rise is 1. Okay, give me 1 to 5 on that. Is that concept making sense? Okay, what about the run? What's the run? 2. How'd you get 2? Okay, because the x coordinates are changing by 2, right? The x coordinates are changing from 2 to 4. So those are the horizontal positions of the points, right? We don't want to be specific about this, though. This is one specific example. In math, specific examples aren't very useful because they only work one time. We want to come up with a general way of saying this that works every time. And so rather than giving these blue points and red points specific coordinates like 2, 1, we're going to do something different. We're going to say that the coordinates of the first point are x1, which just stands for some number, the x coordinate of our first point, and the y coordinate we're going to call y1. What do the subscripts, those ones mean for x1 and y1? Point number 1. They're just going to be the coordinates of the first point that we know. Okay, what do you think we're going to call the coordinates of the second point? Yeah. Whoops, it's, what did I do there? Yeah, there we go. Yeah, because this is the second point, its x and y coordinates we're going to call x2, y2, right? And then what would the rise be? Well, the rise is how far the ant moved vertically in going from the blue point to the red point. Well, that's going to be how much the y coordinates change. Agreed? So try something for me. Tell me how much if the temperature in a room changes from 65 degrees to 70 degrees, how much did it change? 5 degrees. How do you know? Because 70 minus 65, the final value is 70, the initial value is 65. So it changed, the change in temperature was positive 5, meaning it got warmer, right? Okay, what if in a different room the temperature changes from 72 degrees to 68 degrees? Yeah, what do you guys want me to say? Oh, funny, I wonder what that was. I don't know what that would have been, I'm not sure. So what would the rise be there? What's the change in temperature if we go from 72 to 68? -4. Okay, the -4 is important because the temperature changed in a negative direction, meaning did it get warmer or cooler? It got cooler, didn't it? It went from 72 to 68, so it got cooler. And so it's important then that we take the final value, which was 68, minus the starting value, which was 72, right? 68 minus 72 is -4. It gives us the negative there. Everybody get that? Okay, so we're going to do the same thing here. If we're starting at the blue point and ending at the red point, then the rise is just going to be the final y value minus the starting y value. So it's just going to be y2 minus y1, right? Okay, what's the run going to be? the change in x, what's that going to be? x2 minus x1. We want to take the final x value minus the starting x value. And that gives us something you're very familiar with. That gives us the slope formula that you've seen before, right? It's y2 minus y1 over x2 minus x1, which is just rise over run, the vertical change over the horizontal change. Okay, give me 1 to 5 on that. Is that all making sense? Okay. All right, so then if we calculate slopes, there's an infinite number of different possible slopes that lines could have, but we could break them up into basically 4 categories. Okay, one of them is where the slope is positive. If the slope is positive, describe what that line's going to look like, or show me with your arms. What's that line going to look like? Okay, yeah, it's doing this, isn't it, right? What's that mean? So an ant, we use ants a lot in here. Ants walking on the line in the positive x direction, so from left to right, would be walking uphill or downhill? Uphill, yeah, right? So it's going to look like this. And how come? Well, because the rise, if I'm going between 2 points, we need the rise to be positive and the run to be positive. Positive divided by positive is positive, right? Everybody good? Okay, what if the slope is, pick a different number here, we're going to pick purple. What if the slope is negative? An ant walking in the positive x direction from left to right would be walking downhill. Okay, and the reason for that is just that going from left to right, the ant is going to rise by a negative amount and run by a positive amount. And so rise over run, well, what's negative number divided by a positive number? Negative. So I got a negative slope. Okay, what's another possibility? Okay, horizontal line. Okay, how about that one? If I've got a horizontal line, you guys tell me, going between the first point and the second point, what's the rise? 0. Okay, so the slope is going to equal 0 divided by, what's the run? I mean, it could be, we don't know, but it's going to be some number, isn't it? Some positive number. Everybody agree it's going to go, the ant's going to move horizontally. So we'll just say it's some random number. But what's 0 divided by a number? 0, yeah. So this is a slope of 0. How come? Because it has no rise. Okay. What's the other possibility, the fourth possibility? Vertical line. Yep, you got it. Vertical line. Okay, so a vertical line. Let's think about this one. I've got 2 points on the vertical line. If the ant starts at the first point and goes to the second point, what's the rise? Well, I don't know, but some number, right? The ant is going to go some distance vertically. Agreed? Here's the important part. What's the run? 0. The ant, on a vertical line, the ant never moves horizontally at all, right? Okay, that's danger. The universe explodes if we divide by 0, right? So we don't want to do that. It's one of our rules. You can't divide by 0, and so for that reason, there is no slope here. In the past, you might have said no slope for this. What we're going to say now is M is undefined. All right. An undefined slope is a vertical slope, okay? All right, so then last issue for today. What if we want to write equations, we want to put them into slope-intercept form, because that's usually how we want to write our answers. It's really easy, no big deal. You have all the pieces to do this already. All it means to put an equation into slope-intercept form or write it in slope-intercept form just means isolating the y on one side of the equation and simplifying the other side. That's it, okay? So let's look at an example like number 10, okay? What would I have to do in number 10 to put that equation into slope-intercept form? Add 1, okay, because I want to get the y by itself, right? There you go. So I want to leave the y. There's my y that I'm trying to isolate. I've got to get all the other stuff on the other side, right? So to move the 1 to that side, I'm just going to add 1 to both sides. What's the other thing I need to do? Yeah, I got to move the x term. So to move the x term to the other side, I'm just going to subtract 4x from both sides. And what do we get if we do all that stuff? Well, the x terms cancel, the 1's cancel, and so I get y by itself equals 0 plus 1 minus 4x. Well, I'm going to put the x term first, and then the 1, and I got it. Okay, make sense? All right, so now let's graph this thing, because that's the other part of this. How do I graph an equation in slope-intercept form? In fact, how are we going to graph any linear equation in any form? It doesn't matter. It's always the same. How many points are required to define a line? I only need 2. If I have only 2 points, there's an infinite number of points on a line, but to graph the line, I only need 2 of them. If I can find 2 points that are on a line, all I have to do is just connect and extend those points, and I built the line, right? So I need to come up with 2 points to graph the line. How am I going to do that for this equation? Where's the 1 point is given to me automatically. What is it? No. There's a point this is in slope-intercept form, right? So, okay, people are saying 1. I agree. What does that mean? How does that give me a point? Okay, what's the y-intercept of that line, everybody? 1, right? Because it's in the form y equals mx plus b. So b is the constant on the right side. So if we know that b is equal to 1, that just means on the y-axis, I know the y-intercept is 1. I go up 1. Okay, give me thumbs. Ringing a bell? Okay. How am I going to get a second point? Rise over run. I'm going to make a slope triangle. Okay, what is the slope of this line? -4. It's the coefficient of x, right? So if the slope equals -4, we always want to write slopes as a fraction. So what's the denominator? 1. Okay. And here's another important thing. If a slope is negative, we always put the negative sign in the numerator. We're always going to make the denominator positive, and that makes it really easy to graph lines, because that means the run is always positive. It's just the rise that could be positive, meaning up, or run, meaning down. So in this case, how far am I rising from this point? Vertically. If my slope is -4 over 1, what's my rise? Oh, it's -4, isn't it? So if my rise is -4, think what that means. It means I'm going to go up -4. Well, what's that? Down 4. There you go. Okay, so we go down 4, and what's my run? +1. So I go to the right by 1, and I get a second point. And then all I have to do from there is connect and extend. And there's my line. No big deal. Okay, make sense? Okay, how do we do this in my math lab? Have you guys graphed lines? You've graphed lines already, haven't you? Didn't we graph? Yeah, you have on that warm-up assignment. So you know how to do it. You choose the line tool, you put 1 point down, and then you drag it over to a second point to build the line. So you already know how to do that. Let's do one more practice one. How about something like, yeah, let's do that one. Okay, I'm gonna, give me 1 second here. Where's that stuff? What? Oh, there we go. No, I don't want that. There. Why am I not finding my stuff? There it is. Okay. That's what I wanted. Okay, so let's graph a line by putting it in slope-intercept form. So let's take this example. Okay, what do I do? Okay, because what's my goal here if I want to put this into slope-intercept form? Isolate y on the left side. Agree? Okay. So we subtract x. Those guys cancel. I get 3y equals negative x plus 15. Now what? Divide by 3. Okay, now dividing by 3 is the same as multiplying by 1/3. Everybody get that? Okay, so I can do it either way. Like, it's almost easier to think about it. You know, it's up to you, but it's almost easier to think about just distributing a 1/3 through. We'll do it by division. When I divide the right side by 3, remember that if I have multiple terms, that means I'm just dividing everything by 3. Agreed? Okay, so I'm going to divide the first one by 3, the first term, and the second term by 3. Well, this is great because that cancels the 3's. So I get y by itself, which is what I wanted, equals, okay, what's going to be the coefficient of x there? Negative 1/3. Everybody agree? It's going to be, when I simplify that fraction, I've got a negative 1 on the top and a 3 on the bottom. So I'm going to write that as the fraction negative 1/3.